Swayam Prabha. Digital India. Educated India.
So, welcome back everyone, and in this module we will start our discussion on the second part of the angular momentum principle, and we will right away focus on our discussion on the conservation of angular momentum. So far we have looked at conservation principles of energy and the linear momentum, and in this module we will introduce yet another conservation principle, that is the conservation principle of angular momentum. Later on, in few modules later, we will see that all these conservation principles can be beautifully combined into a single idea of the so-called uh, uh, Noether's theorem, when we talk about the analytical techniques of these classical mechanics. So let's start without wasting time. So the second part of the angular momentum principle. Angular momentum principle. So part 2. Okay, so what we have is conservation of angular momentum. Okay, so for an isolated system, the total moment about any point, the total moment about any point A is 0, right? So that is what the conservation principle says, that there is no net torque acting on the system which is isolated. So, or we can write this in the form of a formula that dLA dt is 0. So there is no net torque acting on the system, or LA is constant with respect to time, right? So so another way to write is that the angular momentum for an isolated system, the angular momentum about its center of mass. See, we have taken any point A here. The A could be a special point, that is the center of mass, right? So we can rewrite this result for an isolated system. This is center of mass. So for an isolated system, we see that the angular momentum of the system about its center of mass, or any fixed point is conserved. Angular momentum of the system about its center of mass or any fixed point is conserved, and or we are talking about that the net moment acting upon the center of mass G is 0. Okay. So this is certainly true for some of the examples we have seen in forces involving central fields, right? So let us look at those, revisit those examples. So we are talking about the cases where we are dealing with central field orbits. Okay. So suppose P moves in a central field. P moves in a central field, and my force is Fr is r hat, and let us say our moment this time is K is r cross with F, and in this case this is going to be 0 because our force field is acting along the radial direction, and the direction, so force is parallel to the vector r, and we expect the net moment to be 0. So in that case, our angular momentum can be written as follows. So our L0 is R cross mv, and this is going to be R cross m times v. So we write it using our Newton's. We write the formula for velocity in the polar coordinates here, because it's a central field. So this is R dot R hat plus R theta dot theta hat. And of course, we if we take the cross product of R with R hat, it's the first cross product is going to give us 0, and we see that this is going to be well, m r theta dot well, r is r times r hat, so r theta dot n bar or n hat. So if we are talking about central field, where r hat is the radial direction, theta hat is the tangential direction, and n hat is the direction which is normal to both r hat and theta hat, right? So that is our n hat. So we see that since k naught, the net moment is 0 because of this central field setup, we expect that this quantity L naught is going to be a constant. It's going to be conserved, and that is the angular momentum principle for this central field. So we write the conservation principle as m r square theta dot is equal to L. Okay. So then what do we have? So then let us see let us extend this conservation principle about any axis. So angular momentum conservation about any axis. So if the external force acting on a system, external force acting on a system has no total, external force acting on the system has no total moment about a fixed axis, then the angular momentum about the axis is conserved. Okay, so we have generalized our conservation principle about any axis. So we have that if we have that the projection of the moment about any given axis is 0, then we expect that the angular momentum about that axis is going to be conserved. It's going to be constant. Okay. So then let us look at an example. It's a nice example of the conservation principle, where the problem says we have a particle P of mass m can slide on a smooth table. Well, let me first draw the diagram, and then it will be easier to write the statement. That way, through diagram, the statement will be clearer. So the setup is that we have a smooth table, and the table has a hole in the center, and there is a particle P of mass m. So of course, it will have a weight which is acting on along the downward vertical here, right? And so that's the case, and the particle P is connected to a string which is being pushed. The string is kept tight or taut, such that the particle, when it is rotating, the string is tight. So there is a net tension acting on the string, so that the particle remains tight when it is moving. So then all we have to find is the velocity of this particle and the tension in the string, right? So let us now write the statement. So it's sliding on a smooth horizontal table. table, and P is connected to a light string. P is connected to a light string passing through a smooth hole. P is connected to a light string passing through a smooth hole at O, so that the lower end of the string hangs vertically. The lower end of the string hangs vertically. It hangs vertically below while P moves on top. P moves on top. Essentially, when I talk about movement, the particle is rotating. It never leaves the surface of the table, right? So moves on top with the string taut, right? So we don't want the string to be slack at any given point of time. So then initially the lower end of the string is pulled. The lower end of the string the lower end of the string hangs vertically. It hangs vertically below. The lower end of the string hangs vertically below while P, the particle P, moves on top initially the lower end of the string hangs vertically below. Lower end of the string, something is missing here. Initially the lower end of the string, we have repeated something. So initially the lower end of the string, I'm trying to give the initial conditions here in this statement. So lower end of the string is fixed with P, with the particle P moving with velocity with speed u. So this is the initial velocity or the initial speed. So that's the initial condition. And on a circle with of radius a, right? So this is the last statement which conveys us the initial condition of the setup, right? And we need to find the velocities. So find v of t at any given point of time and the tension t of t at any given point of time. Okay, so we can use the conservation principle, but how? So to do that, let us try and draw the force diagram here. So we have the particle P which is sliding on the table, on a smooth table, so there is no friction, and it is of course moving on a circle. So we have the net weight which is acting downward, right? And of course this is going to be normalized with the normal reaction because the particle is not going to leave the surface of the table. So if we were to write the force balance, we see that let us first note down all the forces. We have the weight of the particle. We also have the normal reaction, and we have the string tension. The weight, the normal reaction, and the string tension. And we see that, let us call the string tension T at r hat. So we have T acting along the radial direction. So that's the vector part here, r hat. And the normal reaction is n times k hat acting vertically, and the weight is minus mg k hat, right? So if we were to do the force balance along the normal direction, there is not a problem. The weight is being balanced by the normal reaction. And so what we have is that the net force along, let us say if this is our center, so this is our normal direction k. So net force along k will be 0 because the normal reaction is going to be balanced with the weight, right? We can because the particle is not is leaving the table. So if that is the case, then we expect that the net moment is also 0 along the k direction. Well, the force is 0, so the moment is 0. Or along this this direction k hat, we have the angular momentum is conserved, L naught. So L naught is conserved. So let us write down what is the angular momentum. So the angular momentum is going to be the formula says this is going to be mr times v phi, or v phi is the tangential component of the velocity. So this is going to be mr square r square, well, v phi is the tangential component, so v phi. So mr v phi, so mr square theta dot. So theta dot is the angular velocity of the particle. So we see that this is going to be a constant L, and we can evaluate L using our initial condition. So at t equal to 0, we saw that the velocity was the distance from the axis of rotation of the particle was a, and the velocity was u. So from here we can get a relation. From this condition we can get a relation that r square theta dot is a times u, or theta dot is au by r square. Theta dot is au by r square. And now we can write down the velocity at any given point of time. So v of t is vr, which is the component, radial component r dot r hat, plus r theta dot theta hat. And of course we can plug in the formula for theta hat here to see that we get this is r dot r hat plus au by r times theta hat. Notice, a thing to notice here in this formula is that v of t goes to infinity when the radius, when the the particle is coming closer and closer to the center. So when r goes to 0, right? So because of this component here, so v of t goes to infinity. Okay, so similarly we can write down the string tension here. So t of r, this is acting radially, it's going to be m times r double dot minus r theta dot square. And we see that this is, we plug everything, we see that this is going to be a square u square by r cube minus r, well, what have we got? So we have to put a minus sign because the tension is acting in the negative r direction. So t of r is minus t of r hat. T of r is minus t of r hat because tension is acting in the negative radial direction. So from here we can balance out this negative sign to see that t of r is this quantity. We plug well, we have a formula for theta dot, we are plugging that, and this is going to be r double dot times m. So that is again the formula for tension, that is what we need. And again we see that this becomes infinite as the distance from the center of the object goes to 0, or the object comes closer and closer to the axis of rotation. Okay, so those are what the problem was expecting. And now we have another nice problem which is quite you will the listeners are going to see this next problem in many of the textbooks, and this is a very simple application of conservation of angular momentum. So the problem says that we have an insect which is on the ball. So the problem is that of a beetle and a ball. Beetle and the ball. Right? So we have an object or a beetle or an insect which is on the ball. At t equal to 0, the beetle is at a point where which lies on the axis of rotation of the ball being a sphere, and we can certainly take the sphere to be a hollow object. The ball is a hollow object, but eventually that doesn't matter in the problem, as we shall see. So the beetle is initially sitting on the axis of rotation at the north pole, which is passing through the axis of rotation, the natural axis, and then the beetle at some given point of time goes to the equator of the ball. So now we have to find out, going from point A to point P, what is the change in the angular momentum of the sphere. And let's say some initial condition is given. The sphere is moving with some initial angular velocity and so on. So we have to find what is the change in the final angular velocity, right? And also the change in the kinetic or the total energy of the system. So that's the problem. Let's write the statement. So a uniform ball of mass m and radius a is pivoted. So pivoted means it is fixed in such a way that it is able to rotate. It's pivoted so that it can turn freely about its diameter, and diameter fixed in vertical position. So a beetle of mass m crawls on the surface of the ball. Initially, so this is the initial condition. Initially, the ball is rotating with an angular velocity. The ball is rotating with an angular speed or angular velocity omega, and with the beetle at the north pole. So all these are initial conditions. This statement is completely the initial condition, and then we have to find what is the part A, the angular velocity, and the part B is the change in the kinetic energy, when the beetle walks down the equator. The beetle walks down the equator. Okay. So what we have is that we can just analyze the different forces acting on the ball and the beetle system. So beetle and the ball can be considered a combined system. So since we have two objects in the system, we will certainly have the respective weights, and also we can talk about the reaction forces of the pivot. But we are going to take the moments in such a way that those reaction forces don't come into the picture, right? So that is an unknown of the problem, which will be cancelled by taking an appropriate by taking the axis of rotation on the pivot itself, which is true. So what we have is, so the forces are of the beetle ball system, so B and B system. We see that the weights, so the forces are the weights of the ball and the beetle, the weights of the ball and the beetle, and the reaction forces at the pivot, at x and y, the reaction forces of the pivot at x and y being, we have, let's say, one pivot point is at x, the other pivot point is at y. So that is where the sphere is moving. Now we can talk about the moment, but we can talk about the moment from about this axis. Let me call this as axis CD. So moments about this axis CD. We can talk about the moments. If that is the case, the beetle is sitting on the axis itself, so the net distance of the beetle from the axis is 0, and the pivots are also the normal reactions of the pivots are also along this axis. So the moments due to the pivots, the pivot forces, the reaction forces of the pivot, and the weight of the beetle is not going to really come into the picture. And so we have, not only that, we don't even have to write the total moments of the system, because we will see that if we consider the beetle and the ball as an isolated system, there is no external force acting on the system. So for an so we will not go through the moments route. We will look at the case where the system is isolated, right? So the system is isolated. So we see that for an isolated system, the angular momentum is conserved. And all we have to do is we need to write the initial angular momentum of the system and the final angular momentum and equate it to find the answer. Okay, so what we see is that the initial angular momentum of the system is, let us write the various angular momentum. The initial angular momentum of the system is given by the angular momentum of the ball, right? So that is of the ball. The beetle is sitting on the axis, so we don't expect anything due to the beetle contribution. So the ball gives us the initial angular momentum is 2 by 5 m a square, a being the radius of the sphere, m being the mass of the sphere, times the angular velocity with which the ball is rotating. So that's due to the initial condition. And then the final angular momentum, we see that this is going to be 2 by 5 m a square. That is the moment of inertia of the ball. And let us call the final angular velocity to be omega. So this is unknown of the system. So this is the ball contribution. And now the beetle has moved on the equator. That is the problem. So the final angular momentum of the beetle now is going to be m times a times the angular velocity. So m times a times the angular velocity is omega times a. So this is the beetle contribution. And we see that the net we can write down. So the net is, so we can equate these two components. So let me call this first expression as A, the second expression as B. We can equate A equal to B, and because of the conservation of angular momentum, and we see that the new angular momentum omega is 2m by 2m plus 5m times omega. So we see that the final angular momentum is less than the initial angular momentum, and we expect that because now the beetle is also contributing. This is an isolated system. The beetle has moved to another region, so that is also adding to the moment of inertia of the system. So the moment of inertia has increased, right? Earlier the moment of inertia was not contributing because of the beetle. So that is the first. And the second part is we have to find the change in the kinetic energy. So all we have to do is, it's all about the rotational kinetic energy. So initially we get that the kinetic energy was half times 2 by 5 m a square times omega square. So that is the initial rotational kinetic energy, and final will be half 2 by 5 ma square times omega square plus half m a omega square. This is due to the beetle, and we plug omega here, and we see that this is going to be minus m times capital M times a square omega square by 2m plus 5m. So we see that the minus sign clearly reflects that the kinetic energy of the system has changed. So that completes this part of this problem, and also we are now over with this. The time is up for this module, and in the next module we will have more such examples related to the conservation principle, the conservation of angular momentum. So thanks so far for listening. Thank you very much.